today. Okay, guys, so now we are ascending the order of hierarchy. So, anatomy and physiology is, as we said, the study of the structure and the function of the living systems. But these living systems are divided into hierarchy. Remember last week we discussed how they used to consider anatomy and physiology at the level of the macroscope. So anatomy and physiology is what you see. If you do not see, they used to assume that it does not exist. Then they realized that what we do not see with our naked eye, the microscope, is in fact there is more of what we don't see that is regulating and controlling what we see. So now there is a reductionist, what is known as a reductionist convention, where we break things down. Then we see what are the building blocks of anatomy and physiology. So, like I said, back in the day, they used to consider anatomy and physiology at the level of the cadaver, the level of the organism, and then with the reductionist or reductionism, we break down an organism into organ systems. The digestive system. We don't call it the stomach system. It is made up of multiple organs. So you have the organ system, then you have the organs. So the organs make the organ system. So the digestive system is made up of multiple organs. It is made up of the esophagus, the oral cavity, the nasal cavity. Many students um, think that how come the nasal cavity isn't only part of the respiratory system, is also part of the digestive system, because you know the feeding tube, okay, for patients with dementia, and they're not able to initiate the peristalsis, and you know, a ripple effect and pushing the food down the esophagus, so they use a feeding tube to physically force the food down. So this system, the digestive system, we don't call it the esophagus system, even though the esophagus is an organ and part of it. The stomach is an organ and a part of it. The intestine is an organ and part of it. But it is not an organ. It is an organ system, is a network. So then we reduce an organism to organ systems, and the organ systems into organs, and the organs, we divide them into tissues. There are multiple tissues that make up the organs, and then the tissues, they are made up of cells. And then they celebrated how cells are the basic unit of life, and cells are the basic unit of death. We are alive because the cells are alive, and we are dead because the cells are dead. We are healthy because the cells are healthy, and we are ill because the cells are ill. And we talked last week about stress attacking the cell, the external versus the internal environment, fighting each other. The external environment, always a source of stress, physical stress, trauma, hyperthermia, hypothermia, the hyperglycemia, hypoglycemia, some chemical stress, some infection. But your body is able to survive and achieve homeostasis due to the built-in systems inside the cell that allow the cell to survive. And we talked about how we have misfolded protein response. These proteins inside the cell that are not folded properly, an alarm would go off that brings in this cellular organelle, the police called the proteasome, the shredder of the misfolded, the messed up proteins. So these types of activities, the cell able to sense that something went wrong, the cell is able to detect something went wrong, and then initiate an input, then integrate the input, then send out an output that is correcting. That's happening in the cell. Then they realize that this pyramid here is missing something that is very important. So now the celebration cannot be complete because even though the more you go down, the more basic you are. So the cell is the most basic, followed by the tissue, followed by the organ, followed by the organ system, followed by the organism. There's something one more here. We're not going to talk about it yet, but it exists. What is on top of the organism? Population. Excellent. So multiple organisms give you a population. Many cells give you a tissue. Many tissues give you organ. Many organs give you organ systems. Many organ systems give you organisms. Many organisms give you a population. Now they realized that even although the cell is the basic unit, there is something that is subcellular. There is a subcellular level. There is a subcellular level. This is the topic of today. This is today's chapter. And that's what we're doing with the microscope next week, looking at the slides. So now we're preparing our understanding of what is the microscope, the greatest invention ever known, because it enabled us to discover everything that sustained life that we cannot see. We only see the tip of the iceberg. What we don't see, what keeps us alive. So the subcellular level is the level of the chemistry of life. The title of today's lecture is The Chemistry of Life. So if you have a cell, the cell cannot sustain life on its own. So if you have an apartment, the apartment is the unit of the building, and many buildings give you a neighborhood. Many neighborhoods give you society. Many societies give you a country. But your apartment does not exist as an apartment. There is carpet in there. There is AC. There is heater. There is kitchen supplies. There is the little stuff that without them, you can never say I have an apartment actually. You can never say I'm going to move into an apartment unless these things are there. So the same thing. You can never say I have a cell unless you have an intact chemistry inside the cell. Unless you have micromolecules. Now that is one subcellular thing. Micromolecules. Unless you have micromolecules. And micromolecules, like the building blocks, like the bricks, come together to give you a wall. So the micromolecules give you macromolecules. So micromolecules clump up and give you macromolecules inside the cells. That's important for metabolism, for energy, for metabolism. We're going to learn about catabolism and anabolism inside the cell. We're going to learn that inside the cell, you got to have enzymes. You got to have enzymes. And you have to have organelles. And you have to have solutes, salts. You got to have salts. You got to have solutes. You got to have electrolytes. These are minuscule subcellular things. They are meaningless if you isolate them. On their own, they mean nothing. A carpet means nothing on its own. But when you carpet the apartment, now you will see its value. AC on its own is meaningless, but when you put it in the home, you see what its value is. Same thing, salt, enzyme, electrolyte, calcium, organelles, micromolecules, lipids, monosaccharides, sugars. These things are all meaningless. But when they are inside the cell, they help the cell stay alive. And then they realize when we get sick, you see somebody coughing, that thing is not, it's at the level of the organism. You can see it. That's why they call it a sign. You can see it. They cannot hide it. But that sign didn't come about at the level of the organism. It began at the level of the cell. Then many cells got necrosis, so you have a tissue. Then you have a problem in the organ. Then in the organ system, then the organism is now holistically is in a state of inflammation, and all the bodily systems are suffering with that ill and sick system. Then they realized that even the cell, when something went wrong, it's these guys, the subcellular. So in cancer, you have a cancer because One enzyme is not doing its job. A tumor suppressor is not doing, and a tumor suppressor is not a cell. A mutation does not happen at the level of the cell, it happens at the subcellular level. So the most important level is the subcellular level. We're going to see how below the cell all the action that allows the cell to survive happen. You're going to see metabolism that happens inside the cell. You're going to see the cell division. You're going to see the different macro and micromolecules, and you're going to see these organelles, and you're going to see how these enzymes, if they do their job too excessively, that's a problem in the cell. If they do it so slowly, not at the proper rate, a problem is going to happen. So now we're going to learn that it is the subcellular, the level below the cell. If subcellular compartment is working perfect, then you will be healthy. If subcellular compartment, something is wrong with it, then the cell is going to be damaged, then the tissue is going to be damaged, then the organ is damaged, then the organ system, then the whole organism coughing and doing all that problems. And all of this was elucidated with what? The microscope. If it wasn't with the microscope, we wouldn't have known that. So biochemistry is the chemistry of the living system. So obviously chemistry is a physical science. You study the empirical formulas, you study the structures of the compounds and the ions. But you know we have a hybrid. Remember last week we said we have a hybrid, a mixture. You have a biophysics, you have a biochemistry. So we study the physics of life and the chemistry of life. So that is biochemistry. So we're going to be in biochemistry studying the molecules that compose the living organisms. We're going to be studying the lipids, the sugars, the nucleic acids, and the proteins. These are the biggest families that help us stay alive, which are the carbohydrates, the fats, the proteins, and the nucleic acids. So we must begin always reductionist. We break things down. You are welcome to go up or down this pyramid as you like, but you have to have it in that order. From there, you can go in a reductionist or a holistic or holist view. You can go up the pyramid or down the pyramid, but you gotta know this pyramid. And that was one of the figures on the study guide for the lab exam. You're gonna see that you have that. I couldn't see it. Yeah, I posted it up on the announcement. It was attached in the announcement. Okay, so you're gonna see that the elements give you compounds and molecules, then the molecules give you the cells, then the cell give you the tissue, then the tissue give you the organ, then the organ give you the organ system. Now, you have to understand, each element in the periodic table, just like you have a social security number, it cannot be shared by somebody else. You have a phone number, it cannot be shared by somebody else. If you change that phone number, it's somebody else, you're calling somebody else. You cannot share it. Two people cannot share it. That's why they call it the atomic number. That's why they call it the I saw an eraser. There's two. Okay. Why do they call it the atomic number? Because that is the number. You know when they say the atomic number, that's the number of the atom. If you call that number, just like your ID number, no two people can have the same ID number. So same thing with the atomic number. So the element must have an atomic number. What is the atomic number? You have to understand that every element must have a nucleus. This is very important. Every element must have a nucleus. And inside the nucleus, there's two things. There's two things. The first thing is the P for plus, for positive. That's the proton. The positive protons. The protons are positive. And inside the other half is N for neutral. Neutrons. They are zero. They are not positive or negative. They are not positive or negative. And around the nucleus, you have orbits. You have valence shells. These shells, who's spinning around the nucleus like the planets spinning around the sun? These are known as excellent negative electrons. Electrons are negative. Electrons are negative. Protons are stationary in there with a positive charge. While electrons are negatively charged. So what is the atomic number? The atomic number is the number of protons. How many protons inside the nucleus? So the atomic number equals the number of protons inside the nucleus. So I don't need to tell you both. I can just tell you the number of proton for this element is 1. You already know that's the atomic number. Or I can tell you the other way around. The atomic number for this element is 1. You already know that's the number of the proton. Remember last week we did inductive and deductive reasoning? So in deductive reasoning, you have a premise. All whales have hair. All mammals have hair. Whales are mammals, then all mammals have hair. So you deduce. So same thing. The proton number is the number of the atoms. The number of the atoms is the number of the protons. So if I tell you 5 is the number of the proton, you deduce with deductive reasoning that that is the atomic number. Then what is the mass number? What is the mass number? The mass number is the sum of the protons plus the neutrons. So that means I can have 3 hydrogens. I can have 3 hydrogen atoms. One with a mass number 1. One with a mass number 1. The other one with a mass number 2. The third one with a mass number 3. Now, what does that tell you? What is the mass number for hydrogen 1? What is the mass number for that? What is the mass number for hydrogen 1? 1. So the mass number is 1, which means protons plus neutrons must equal how much? 1. And I already know, excuse me, I'm sorry. If the mass number is 1, and I know that every element gotta have an atomic number. So what's the atomic number for hydrogen is 1. So for H1, the atomic number is 1. The mass number is 1. What is the number of the neutrons? 0. So H1 has 0 neutrons and 1 proton. Let's go to H2. What is the mass number of H2? It's 2. How many protons does H2 have? 1. How many neutrons does it have? because the mass is 2, so mass minus proton will give you neutron. So that shows you it has, here H1 has 1 proton and neutron 0. H2 has 1 proton and 1 neutron. For 3, the mass number is 3. 1. The mass number is 3. The proton number is, so that means I can never change the number of proton. If you change from 1 to 2, you're no longer hydrogen. You're another atom, another element. So that one always the same. So the proton is 1. Proton number is 1 for all of them. But the mass number is 3 because the neutron equals 2. So the proton number and the atomic number are the same thing. So now what does that tell you? 3 different elements with 3 different mass number. What do we call those?
Isotopes.
Isotopes. Excellent. So isotopes have the same atomic number. They are the same. They have the same like a family member. They have the same last name, but they are different. They look different. One is malnutrition, one is obese, and one is normal weight. But they are the same last name. Same thing. Hydrogen, they are the same atomic number. You change the atomic number, you change the whole element. So each, if you look at the slides, each is identified by an atomic number. That is the number of protons in the nucleus. The periodic table arranges the elements represented as 1 to 2 letter symbols by the atomic number. There are 91 naturally occurring elements, but 24 are in our body. They are bioavailable, bioactive. The rest, they are not bioactive, but that means they have nothing to do with life. No, they sustain life in a different, indirect way. They are part of nutrition. They are part of, to help us, because to stay alive, you need to breathe, you need to survive. So they do other things to help us, but they are not part of the body. So not everybody's a doctor. There's police officer, there is a, construction worker, but they are still a very important part of life. So same thing, once in our body, there are 24, 6 of them are the most abundant. Oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. These are the ones that are very important. That's where you have hyperoxemia, too much oxygen, hypoxemia, too little oxygen, hyper, too much hydrogen, that's acidity, acidic, acidosis, too little hydrogen, alkalosis, too much calcium, hypercalcemia, too little calcium, hypocalcemia. And there are trace elements. Trace elements are found in minute amounts. Some elements are minerals. Minerals meaning that they are inorganic. They have no carbon in them. If you have carbon in you, that makes you organic. If you have no carbon, that makes you inorganic. And they are extracted from the soil plant. So 4% of the body weight is mostly calcium and phosphorus. And the body structure, bones, teeth, enzyme function, nerve, muscle, and cell functions, they need that inorganic part. So atom is, we talked about that plus is proton, neutron. There we go. So this is the Bohr model. Does the cell look like that? If you look there, does the cell look exactly like that? No, that's a model. What are models? Models are simplified representations. You will say, how can I get to school? You'd be like, make an L shape, straight and then right. Is it really an L shape? It's not an L shape, but that just helps you understand. How do the planet and sun look like? See, like a big ball with a little ball, a couple of balls rotating around it. Is that really what happens? No, but that helps us understand. So that Bohr model is a model is a simplified way for us to understand a complex thing that our mind cannot process. Okay? You know, people say heaven. You know, so when you say heaven, did somebody say heaven? No, but you have the idea. It's the garden. You know, the Garden of Eve and the fruits and the orchard and all that stuff is a model. It to represent for you how things look like. Fish heaven. When the fish dies, go to fish heaven. Somebody know what fish heaven looks like? So it's a model. So the same thing is for you to see this Bohr model is to give you like the atoms look like a planet. Okay, so let's look at carbon. Please, you got to be able, if you look there, please, there's no projector here. So the projector is in, so if you see where my mouse is, the carbon has 6p plus, so that knows the atomic number. They don't got to tell you that. The atomic number is 6. The atomic mass is 6 plus 6 nitrogen. So the nitrogen plus the proton will give you the atomic mass. The sodium has 11. You see that's his different number. Atomic number is P. Yeah, the atomic number is 11, so that's 11P plus. And the electrons are E minus. So that shows you a quantum model where you see a cloud. They are spinning so fast that they make like a cloud around the nucleus. Isotopes, you guys were excellent. You knew those. These are varieties based on what? On mass number. They are varieties of an element that differ only in the number of the neutrons and therefore in atomic mass. So there are extra neutrons that increase the atomic weight. Extra neutrons that increase the atomic weight. So isotopes of, so you know this mass and weight, don't let it confuse you. Oh my God, he said atomic mass. Now it's atomic weight. It's the same thing, mass and weight. So isotopes of an element are chemically similar because they have the same number of valence electrons. So the atomic weight is the relative atomic mass of an element, and it accounts for the fact that an element is a mixture of isotopes. So that's what we just talked about on the board. If you see where my mouse is, see the mouse? Hydrogen H1, it has one proton. No, neutron is this orange. So H1 has no orange. So it's just red. That's a hydrogen proton. It has one electron. Deuterium, it has two. The atomic mass is 2 because one proton, you see for the 3 is one proton. One proton, one proton, one proton. But for H1, one proton, 0 neutron. For H2 is one proton, one neutron. And for H3 is one proton and 2 neutrons. You can have as many neutrons as you like, but if you change the number of protons, you're no longer the same. Yes?
So what's the atomic number for deuterium?
Is the same. Is hydrogen. The atomic number is 1 for all of them. You see where my mouse is?
Change to deuterium instead of hydrogen.
It didn't change. It's still deuterium is a hydrogen.
Right, I'm saying that's the isotope.
The isotope, yeah, because it has a different mass number. So that's a sibling. They have siblings, but the atomic number can never be changed. Can never be changed. Isotopes of an element have identical chemical behavior, but they can differ in their physical behavior. So radioisotopes are unstable isotopes that decay and radiate. They give off radiation in a process called radioactivity. So every element has at least one radioisotope. So intense radiation can be ionizing, known as ionizing radiation. That's stressful to the skin. It ejects electrons, destroys molecules, and creates free radicals. These free radicals are dangerous because they have extra lone pair of electrons. So actually we use these free radicals in the immune system. So when the macrophage, these police cells, the macrophages, the monocytes, the neutrophils, the eosinophils, when they want to destroy a bacteria or a fungi, they send the weapon, the reactive oxidative species, the free radical, to kill the bacteria. But you drinking the alcohol, that's going to increase reactive oxidative species to you, not the bacteria. It's going to hurt your own body. And that's how you destroy the liver and you have alcoholic liver disease. Same thing with the nicotine. Same thing with smoking the weed, the cannabinoids. One of my students said, I'm sorry, professor, I'm not going to stop the weed. I said, it's dangerous. He said, I'm sorry, but I'm not stopping the weed. It's my stress relief. There are other alternative, much better stress relievers than the weed with the cannabinoids because it's going to cause misfolded proteins in the brain, like mad cow disease.
Oh, what is that?
So that is when there are improperly folded.
What things? So there's other things. What are the other things?
Other things. It's from person to person. Like find something that you enjoy. You develop a hobby that is lucrative for you. Something that can your profession. Something that is beneficial than smoking a weed. Somebody said something. Something easier. Something better. Easier and better. Physical half-life of exercise, sports. Okay, so there's a biological half-life and a physical half-life. So the physical half-life of radioisotopes is the time required for 50% to decay to a stable state. And the biological half-life of radioisotopes is the time required for 50% to disappear from the body. Standard measure of radiation dosage is the sievert. So that just shows you the radiation. This is very important slide because that shows you Madame Curie. So Madame Curie was the first woman to receive a Nobel Prize. And I think her daughter did also. And she died, she funded her own research. So she saved up the money and she funded her own research and she advanced scientific research and she helped us, but she paid the price and she died because of the radioactive poisoning. She was a brilliant woman. She died at the age of 67. Okay, but her daughter continued her legacy. I think her daughter also won a Nobel Prize. Okay, ions. An ion is a charged particle, an atom or a molecule with unequal number of protons and electrons. So ionization is the transfer of electrons from one atom to another. That is ionization. Anion is a particle that has a net negative charge due to the gain of electrons. And a cation is a particle that has a net positive charge due to the loss of electrons. So ions with opposite charges are attracted. This is a very important concept, guys. So there is the concept of bonding. So we know that water is H2O. That's a bond. You know, when people get married, the husband and the wife they bond, they call that kind of bond marriage. But H2O, we don't say they are married. They have different types of names. So now let's look at how do molecules bind each other. There are different types of ways these chemicals can bind one another. So you have, for example, two molecules, sodium and chloride. Each one is going to share an electron. That's how they bind. You know, it's very counterintuitive because when your bank account is minus, that means you lost money. But when it's plus, it means you gain money. not for the cell. If the cell is minus, if the atom is minus, it means it gain electron. Their dollar is not a dollar plus, it's a minus electron. That's their dollar. So an element that has Cl minus, that one got paid an electron. They don't get paid in dollars, they get paid in electron. So don't feel bad for the one with the minus. Feel bad for the one with the plus. So when sodium chloride breaks off, becomes Na plus, Cl minus, somebody will say, oh, that one is plus. That one got a net plus, and that one is losing minus. No, the one that's plus is the one that lost an electron. And the chloride, the real one with the plus, is the one who got a plus minus, got a plus electron. It got paid with the one electron. Some of them get paid two, minus two now. They got two electrons now. They got paid more. Some of them they got minus three. They got paid three electrons. So the language between the elements is the electron because they are the ones spinning around. They cannot give the plus. The plus is trapped. Trapped inside what? The nucleus. The plus the proton is trapped inside the nucleus. You cannot get it out. The one that is floating out is the minus. So now, originally, these guys, they're not plus or minus. They are neutral because they are in a relationship. Once they get divorced, when they break, one always take more than the other. Just like how it happens in real life. That is very true. One always ends up with more than the other, even though they say it's half. All the time, one of them gets more than the other. Anyways, in sodium chloride, when you put sodium chloride in water, water is a polar solvent. Water looks like two hydrogens and a very big oxygen. Very big oxygen. Very big oxygen and two tiny hydrogens. Now, what happens is, imagine you and your friend bought a car. You pay 10,000, your friend paid 10,000. So you gotta have the car one day, your friend one day. You're 1 week, your friend 1 week. You're 1 month, your friend 1 month. But let's say your friend, he take the car 11 months, give it to you 1 month. Take it 10 days, give it to you 1 day. Give it 10 hours, give it to you 1 hour. So that is now not an equal. So that is a polar. That is, so the same thing here. Oxygen is so big, it's gonna steal the electrons from the hydrogen. So electrons are gonna be spending more time around the oxygen because oxygen is so big. So oxygen is gonna be more electronegative. It's gonna be more electronegative. And the hydrogen is gonna be more electropositive. And electrons are gonna be flowing toward the oxygen. Same thing. Electrons are going to be stolen from the hydrogen to the oxygen. So the hydrogen is always going to have a plus charge on it because it lost. Because all the time, hey, I want to hang out with my friend. He bought a new car with his friend. Your friend says, well, the car, he didn't give it to me yet. So the car is always with the other big one. So here's the electron. They are sharing them. These are bonds. They are shared, but they are not shared equally. That's why we call them non-polar. These are what we call them polar. So the relationship is polarized to one side. So oxygen is always, electrons are more polarized to the oxygen. The car is always polarized, staying all the time with the big one, not the small one. So that is a polar bond. But this is an example of a non-polar bond. Like here, like chloride and sodium, they are equal. They are equal. So electrons get to stay around both of them with the equal amount. So when you share electrons, what do we call that? Covalent bond. That's a covalent bond. This is, I give you one electron, $10,000. You give one electron, $10,000. We share 20,000 equally. But here, oxygen says, I give one electron 10,000. Hydrogen will give 10,000. and we don't share it equally. We don't share it equally. Still covalent. Don't say ionic. Who said ionic? No, ionic is different. If you're sharing electrons, you're covalent. So you could be covalent polar, you're covalent non-polar. Where?
Positive and negative.
Between who and who?
Hydrogen and oxygen.
No, they are not all positive and negative. They are sharing the electrons, but the electrons are shifting to the oxygen, giving a slight positive charge to the hydrogen and a slight negative charge to the oxygen, but they're sharing electrons. They're not sharing charges. That is, like for example, you buy the food, but you're eating more, your friend is eating on it. You bought one, let's say you bought a week-long supply of food. Your friend, who supposedly paid half just like you, has the fridge. You only have access to the fridge one day. So most of the week, he's full, you're hungry. But if the fridge is yours equal. So the same thing. It's covalent, but it's polarized to the oxygen. But these guys still covalent, but is non-polar. So covalent bond is could be polar covalent and non-polar covalent, meaning that they polar covalent and non-polar covalent, but they're sharing electrons. Sometimes you're not sharing, like that's ionic. We're gonna get to that. Is when you're not sharing, when you are doing, is like when they are flirting. They don't have a bond, they have extramarital stuff. That's ionic. But covalent is when we're actually bonded together with electron. And the water does that, does the ionic bond. So what happens is when you put NaCl in water, what happens now is oxygen is gonna say, sodium always has a plus charge, and chloride is minus charge. That's how they bond together. The oxygen is the most electronegative because it stole from the hydrogen. Very good. So the oxygen is going to say to the sodium, listen, you're bonded with chloride. You think he has electrons. Come look at my electrons. So now they're going to break the bond, and oxygen is going to bind with sodium. The minus oxygen, the electronegative minus oxygen, is going to bind with the sodium. And the hydrogen is going to say, chloride, you're minus, I am positive, bind with me. And that's how we dissolve. That's how we dissolve. This initial bond, NaCl, that was not covalent. That was not a covalent bond. That was an ionic bond because the sodium gave chloride money, gave chloride electron, but it didn't get anything back. Do you understand me? An example of a polar covalent bond is water. Non-polar is like glucose. You have carbon with something, they are shared equally. But here, sodium chloride, the bond is not sharing electron. The bond is sodium gave electron to the chloride. Okay, so in sodium chloride, that is an example of ionic bond. Ionic bond. In sodium chloride, NaCl. In NaCl, the bond is made, one is losing, one is gaining. Chloride, sodium is going to give chloride an electron. So now the chloride is minus and sodium lost. That's the nature of the bond. Exactly. Is when the guy goes. Yeah. Shared equally. By the way, this is still shared equally. It's just polarized. Each one is giving in the sense that each one is giving one. But here, chloride didn't give sodium nothing. Sodium lost an electron to chloride. So if you lose, that makes you cation. If you lose, you become positive plus cation. If you lose like sodium, you become cation. But if you gain an electron, that makes you an anion.
This is bright field microscope. The micro. Yeah. Which one is better, right? Yeah. Yeah.
That's why I said, to tell everyone. That day, half of y'all already.
Yeah. Cation is when you lose an electron. Yes.
I just need some clarity.
Mhm.
Covalent bond, the one polar and polar,
Mhm.
it can be equal sharing and unequal sharing, or it's both.
When you are sharing electron, each one is putting up $10,000. Each one is putting up an electron. You did put it, but in one cases they are honest. You take 50%, you take 50%. In the other case, you still put up half, but that person is taking more than what they should. So in water, hydrogen gave one electron, oxygen gave one electron, but oxygen is taking the two electrons to his side more than hydrogen does. Yeah,
Just one is one to the other.
yeah, it's equal donation. Each one is giving in one electron, but oxygen is pulling the electrons more to his side than the hydrogen because hydrogen is too small. The atomic number is smaller.
I want to know what's the polar share.
Polar is when you polarize, when the relationship is equal, but still like what I said. You buy a car, 10,000, 10,000. The deal is you use it 6 months and the friend uses it 6 months. Both of you pay 10,000. So if you stick to the plan, you use it 6 months, the friend uses 6 months, that is non-polar because both of you have it. Polar is when one uses it for 10 months and give you only 2 months. So now you still spend the 10,000, but the deal polarized more to the big one, to the bully. Yeah, even though both you share. That's covalent. Covalent, you look at, are they sharing the same? They are sharing the same. Whether or not the electrons remain as they should, that will tell you if it's polar or non-polar. So that shows you, look at ionization. So this electron, you look at where my mouse is. This electron right here left from here to here. So that's chloride. If you look at chloride, it has 17 protons, red, 18 neutrons, blue, 17 electrons.
Because the ones that is supposed to be 8 in all, when it comes down to the challenge shell, right?
Yeah.
So the one that's left, because it wants to get down, so it's gonna go to the other one.
It's gonna donate it. It's gonna become positive because it lost an electron, and this one gained a minus, so it's gonna become negative. So now you see it got smaller. You see, if you look at where my mouse is, it got smaller, and now it used to have 11 proton, 12 neutron, 11 electron. Now look at what it has now. It has now 10 electrons because it lost one to chloride. So the chloride is the, if you look there to where my mouse is, that will show you which one is an anion and which one is a cation. Salts. Salts are electrically neutral compounds of cations and anions. But when you put them in a solution, they dissociate in water into ions and act as electrolytes, like sodium chloride, calcium chloride. Electrolytes, these are substances that ionize in water and form solutions that are capable of conducting electric current. So the functions of the electrolytes, the functions of the electrolytes. There's chemical reactivity, osmotic effects, electrical excitability of nerve and the muscle. Electrolytes balance is one of the most important considerations in patient care. So imbalances can lead to coma or cardiac arrest. So we need to ensure that we have the proper balance of the electrolytes. We talked about free radicals. These are unstable, highly reactive particles with an unusual number of electrons. They are produced by normal metabolic reactions, radiation, certain chemicals, and they trigger reactions that destroy the molecules and can cause cancer and the death of the heart tissue and aging. This is known as superoxide ion. The superoxide ion. Antioxidants are chemicals that neutralize free radicals. They make them lose this extra lone pair of electrons that make them so harmful and dangerous. Where do we get the free radicals from? We get them from radiation, we get them from metabolic reactions, and we get them from certain chemicals. They trigger reactions that destroy the molecules and can cause cancer, death of the heart tissue, and aging. So an example would be superoxide ion, anion. Antioxidants are chemicals that neutralize the free radicals. So example would be superoxide dismutase. That's an antioxidant enzyme. It converts superoxide anion into oxygen and hydrogen peroxide. So selenium, vitamin E, vitamin C, and carotenoids are antioxidants obtained through diet. So atoms can combine to form molecules. We have seen that. Elements coming together giving you a molecule. So two hydrogens come together with an oxygen to give you water. So water is a molecule. So the molecule particle is composed of two or more atoms united by a chemical bond. So the compound is a molecule composed of two or more different elements. It can be represented by a molecular formula which identifies the constituent elements and how many atoms of each are present. It also can be represented by a structural formula which identifies the location of each atom. Isomers are molecules with identical molecular formula, but they have different arrangements of their atoms. So if you look here, look at the structural formula, the condensed structural formula, and the molecular formula. The molecular formula for ethanol and ethyl ether is the same. You see my mouse? Both of them have how many carbons? Both have how many hydrogen? Both have how many oxygen? But even though they have the same, they are structured differently. So in ethanol, you have the oxygen with the hydrogen, but in the ethyl ether, you have the oxygen in the middle. So the structural formula is where exactly is each element located. The condensed formula is similar to the structural formula. It shows you how they are. You see in the structural formula, you have CH3. See where the mouse? CH3 in the middle, CH2, the OH is to the side. While here the O is in the middle, it puts the O in the middle. But the molecular formula, it does not, you cannot tell how it looks like just by looking at the molecular formula. So the molecular weight of a compound is the sum of the atomic weight of its atoms. So example is to calculate the molecular weight of glucose. You have 6 carbons of, that's a typo. That's a typo. It's not 66, it's a 6. You have 6 carbon atoms multiplied by, each carbon atom is worth 6 atomic mass units, AMUs. So you multiply 6 times 12, that would give you 72 AMUs. So that's all how much do the carbons weigh. It's like when you have a salad. I have 2 tomatoes, lettuce, I have 3 cucumbers, and I have 1 cabbage. How much does my salad weigh? You see, I have 2 tomatoes, I got to put that out. How much each tomato weigh? How much the whole cabbage weigh? How much the lettuce weigh? And then I add that together. So in the molecule, they are chopped up, but then I separate them. So as you see here, to calculate the molecular weight, I multiply the carbon by the number of carbon atoms by the mass, and the mass is atomic mass unit, and the hydrogens by the 1 atomic mass, because we already know that hydrogen has an atomic number of 1, and oxygen has 16 atomic mass units. So you multiply by 6, then you add up everything together to get 180. Chemical bonds hold together within a molecule or attract one molecule to another. So there are ionic bonds. We talked about those. See where my mouse is. The ionic bonds is an attraction of a cation to an anion. One who lost an electron to one who gained an electron. Is when you give somebody a gift. You lost money and they gained the money, but they appreciate, supposedly, that gift. So now you have a bond that is not based on sharing. And for example, in marriage, one pays this money, one pays that money. They share them together to buy a house. So here each one is supposedly paying a share. But in ionic, it's like from one to the other. You're giving you're giving your electron, like in sodium and chloride. Covalent bonds. Covalent bonds are atoms that share one or more pairs of electrons. So there's a single covalent bond where you have a nuclei that share one pair of electrons, and a double covalent bond where a nuclei share 2 pairs of electrons. Sometimes you have a triple covalent bond, and that is when nuclei share 3 pairs now, not 2, 3 pairs. So if electrons are shared equally, it's a nonpolar covalent bond. That's what we talked about. When the electrons are shared equally, it is nonpolar. For example, carbons binding together. That's an example of, if you look at here, this is an example. You see where my mouse is? This here is a non-polar covalent bond because they're sharing them equally. It's not like they're more gravitating to this side or that side. They're equally shared. But if electrons are shared unequally, do you guys see what I'm pointing with the mouse? If they are shared unequally, it is a polar covalent bond. An example would be hydrogen bonding with oxygen. And electrons spend more time by oxygen. So if you look at two hydrogens, you see these guys are shared equally. One is giving one is giving one, so they are shared equally. Oxygen atom, carbon atom, and oxygen atom. Look at how they are binding. So they are sharing 2 pairs. They are sharing 2 pairs on each side. The central carbon atom, that's carbon dioxide. So each oxygen is sharing 2 pairs of electrons with the central carbon. What kind of an example, what kind of bond is that? Is it polar or non-polar? Non-polar, because the electrons are not gravitating to the oxygen side or the carbon, because you know now carbon is almost as big as oxygen. If this was hydrogen, hydrogen is too small. That's why you're not supposed to have a contract between somebody underage and somebody over the age, because they will polarize the contract. But when you have two of them that are over the age, you will see that they will share that they will be equal. There will be non-polar. It will be shared equally. So there we go. That's what we drew. So non-polar and polar covalent bonds. So the non-polar covalent bond is a bond that is shared equally. And the polar, you see one is more electronegative while the other one is more electropositive. So electrons are more around the oxygen. Molecules and chemical bonds. So a hydrogen bond is a weak attraction. No, that's a different type of a bond. Hydrogen bond is a weak attraction between a slightly positive hydrogen atom in one molecule and a slightly negative oxygen or nitrogen atom in another molecule. So there are relatively weak bonds, but very important to physiology. So water molecules are attracted to each other by hydrogen bonds. So it looks like that when it comes to water. So how does water look like before you drop salt in the solution? What does the water look like before you drop in the solution? So before you drop salt, you have water look like that, H2O. 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 H is in this water.
Yes.
Now, what kind of bond is in blue? What kind of bond is in blue here? What kind of bond is that? I'm sorry? When I say what kind of bond, we begin big. Is it ionic? Is it covalent? Is it hydrogen bond? What is it?
Hydrogen. No, covalent.
Ionic, did one give to the other?
Covalent.
That's covalent. Now you have to be more specific. We don't just have covalent, we have covalent polar versus non-polar. So is it every covalent bond you have to identify? Don't just say covalent. Is it covalent polar or covalent non-polar? It's covalent. How non-polar? We just said that all the electrons gravitate always to the oxygen because he's so big. Look here. If you look at this slide. Look at where my mouse is. Look at the mouse. You see this is oxygen, that's hydrogen. The bubble around the hydrogen is so small, while the bubble around the oxygen is so big. You get that? So now here, that's an example of a polar covalent bond. That's in the cup, in the solution. Do you think that's how the water look like in solution? It looks like that only? No. This oxygen is electronegative. This is electropositive. That's electropositive. That's electronegative. That's electropositive. That's electropositive. That's electropositive. That's electropositive. That's electronegative. That's electropositive. That's electropositive. That's electronegative. That's electropositive. That's electropositive. That's electronegative.
Ionized.
Do not ionize because there's nothing to ionize. They don't ionize themselves.
If the salt.
If there is, but there isn't.
The salt is in it, or I'm sorry.
Then the next step is while they are like that, what happens now is this oxygen. What charge is this oxygen?
Negative.
What charge is the oxygen? Is electronegative. What charge is the hydrogen?
Positive.
So the oxygen of one water is going to start flirting with the plus hydrogen of the other water. So you see, there are many H2Os, but they're not going to stick to one relationship. So they're going to, now this O minus is going to start making relationship with the other water, hydrogen plus. This O minus is going to start to have H relationship because you know minus plus. You know the people in the society is not just a husband and a wife. Sometimes they have extramarital kind of relationship. That's what's happening here. So now they are in this covalent bond. In addition, they are always having side dotted with the opposite charge. So this is plus is going to have a dotted relationship with the O. H is going to have a dotted relationship. The plus is going to have a relationship with the minus. The minus is going to have it's like that. So it's not just one type of bond in water, the covalent. There is also this dotted weak bond. That's the hydrogen bond. So if there is a bond that is straight line, this is called intramolecular because it's inside the molecule, right? So this is water molecule number 1. That's water molecule number 2. That's water molecule number 3. That's water molecule number 4. That's water molecule number 5. So inside the water molecule, these are the two hydrogens. So there is two relationships. There is an intra, inside, and there is intermolecular, between 1 and 4. So this oxygen is in relationship intramolecularly with these two hydrogens and intermolecularly with the hydrogen of oxygen 4. You get it? I'm sorry?
So pretty much opposite attract.
Yeah, but they attract in two different forms. They attract intermolecularly, that is covalent. So intermolecular, that is known as covalent, intermolecular, and intramolecular, that is hydrogen bonding. So when you drop the salt, that's how they're gonna solvate it. They're gonna start to break down the sodium chloride, and they're gonna start to develop new intermolecular and intramolecular. So you need to tell that the dotted line is between two different molecules and is a hydrogen bond. And you need to know that if it's inside the molecule is intra is inside, inter is between two. So intra is from state to state, California to New York. Inter is international, it's like from US to Europe or to Africa or to China. So this dotted relationship is inter, between two different molecules. Intra is within the same molecule. So this hydrogen bond is a weak attraction between a slightly positive hydrogen atom in one molecule and a slightly negative oxygen or nitrogen atom in another atom. So there are relatively weak bonds, but they are very important to physiology. So water molecules are attracted to each other by hydrogen bonds. So the large molecules, DNA and proteins, are shaped in part by the formation of hydrogen bonds. You see, that's what we drew. You see the mouse? You got to look there. You see the mouse? So already this dotted line representing intramolecular, and this strong line representing intermolecular. And you see the big line, the dark line is covalent. You see? The intramolecular is covalent, while the intermolecular is hydrogen bond. Very good. Van der Waals are weak, brief. They are timely based attractions between neutral atoms. There's fluctuation in electron density within an atom. It creates polarity for a moment and attracts the adjacent atom for a very short time. Only 1% is as strong as the covalent bond, but they play important role in physiology. For example, the protein folding. So we need these van der Waals to fold proteins on themselves. So the body fluids are complex mixtures of chemicals, and mixtures consist of substances that are physically blended but not chemically combined. Each substance retains its own chemical properties. Like in a salad, you can see the tomato, you can see the lettuce, you can see the cabbage, you can see the green peppers. So they're not completely blended, they are mixed. They're mixed together. So most mixtures in our body consist of chemicals dissolved or suspended in water. So water is 50 to 75% of the body weight. There are polar covalent bonds, and a V shape give water a set of properties. So this water has many important properties that make it important for life. You know, they say they found life in Mars because they found water. So now water is the universal symbol of life. If there is water, there is life. If water come out somewhere in the desert, the birds are going to start coming to that site. So water is the sign of the life. Why is that? Number one, Water is a versatile solvent. It will dissolve. It will dissolve all of the other solvents, all of the other solutes. So it does not mean it dissolves everything. Water does not dissolve every single solute out there. Water does not dissolve oil. But if you compare water to any other solvent, it dissolves more than it. You know, they say in the jail, which murderer killed the most? They won't say I killed 10, I killed 5, I killed 15, I killed 20. Water, when compared to all the other solvents, it dissolved most than anybody. Nobody dissolves more than water. But it doesn't mean it killed everybody. Doesn't mean it dissolved everybody, but it dissolved more than anybody else. The number one dissolver ever. Number two is cohesion. That is what I'm talking about. These inter and intramolecular forces happening at once. Not many substances enjoy the property of having two types of attractants in one. Inter and intramolecular, hydrogen and covalent. Water can. And that causes cohesion. We need that in our body. The serous fluid around your heart, it is liquidy with water. So it's very important for adhesion. It sticks. It sticks to your lung, sticks to your water, sticks to your lung, sticks to your heart tissue, and protects it like a cushion from trauma, from damage, protects the body, visceral, soft organs. Who told you to do that?
That's what they're saying, it's supposed to put salt on the water.
If you want to get salt poisoning, or if you want to get high blood pressure, you don't have to put salt in the water. It depends on, you remember we said there's pH. Everything in the body, this has to be in balance. The salt has to be in balance. The minerals have to be in balance. The glucose have to be in balance. So you cannot say you're supposed to put something, sugar in water or salt in water. No, you drink water as pure water. If you need salt, obviously put salt. If you don't need salt, then don't put the salt. Then there's thermal stability. Water has a high specific heat capacity. Water it takes a lot of fire to make water evaporate. Water is oxygen and two hydrogen. Simple to ammonia, NH2. But ammonia will long evaporate at very cold temperature compared to ammonia would evaporate at 2 degrees Celsius. But water would evaporate at 100, even though both are, this one is H2O, that one is H2N. Ammonia is nitrogen with two hydrogens, and water is oxygen with two hydrogens. They have the same molecular mass, but this one will evaporate in very hot, 100 degrees Celsius, while this one will evaporate at 2 degrees Celsius in a perfume. Why? Because the thermal stability of water. That's why we use water in sweat, because water is like a shield, sunscreen and thermal screen. It takes a lot of heat to make the water evaporate. Water does not evaporate easily. So the solvency, ability to dissolve other chemicals. Water is a universal solvent because it dissolves more substances than any other solvent. There are metabolic reactions that depend on the solvency of water. Hydrophobic substances dissolve in water. Hydrophilic. Philic meaning love. Phobic means fear. Hydro means water. So hydrophilic means you can dissolve in water. Water, like, dissolve, like. Birds of the same feather flock together. If you are a salt, you are polar, you dissolve in water. Proteins with amino acids that are polar amino acids dissolve in water. But hydrophobic, like you guys said, oil does not dissolve in water because it is hydrophobic. So to be soluble in water, a molecule must be polarized or charged. That's what happens in the liver. with these CP, with these liver enzymes known as P450 enzymes. When you have waste and you have a drug that you took in your body, you want to metabolize it and you want to get rid of it from the body, you convert it from lipid soluble into water soluble. So attractions to water overpower the ionic bond in the sodium chloride, and water forms hydration spheres around each ion, and the salt dissolves. So the water negative pole faces the sodium, and its positive pole faces the chloride. There we go. Let's look at that sodium plus. First of all, look at A. You see where my mouse is? Look at A first. The red is the electronegative. So who's red? Oxygen is the red. That's the electronegative, oxygen. Who are the two little positive blues? So sodium is plus. So who's going to be facing it? The minus red or the blue plus? The minus red. But look at chloride, who's minus. Who's going to be facing it? The plus blues or the minus red? You see, that's how we dissolve in water. The oxygen is going to surround the sodium, and the hydrogen is going to surround the. Okay. Adhesion is the tendency of one substance to cling together. Water adheres to membranes, reducing friction around the organs. So around your heart, you have a water serous membrane. So when your heart is beating and hitting your rib cage, it doesn't rupture, doesn't get injured, because it has a capsule of water membrane surrounding it. Cohesion is the tendency of molecules of the same substance to cling to each other. So water is very cohesive due its hydrogen bond. So the surface film on the surface of water is due to molecules being held together by the surface tension. And chemical reactivity. Chemical reactivity is the ability to participate in chemical reactions. So water ionizes into H plus and OH minus. So the ionization of water can also be seen in ionizing other chemicals, acids and salts. So it involves the hydrolysis and the dehydration synthesis reactions. We're going to talk about those. How if we want to go from macromolecule to micromolecule, we use water to separate. You see, if you have a brick wall, you break it with a hammer, but in the molecules, we use water to separate this big polysaccharide into little glucose. In this big lactose, we separate it with water into glucose and galactose. This big maltose, we separate it with water into glucose and fructose. This big sucrose, we separate it using water into glucose and glucose. Water has high thermal stability due to high heat capacity. So the amount of heat needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So a calorie is the base unit of heat. So 1 calorie is the amount of heat to raise the temperature of 1 gram of water by 1 degree Celsius. Water stabilizes the internal temperature, and hydrogen bonds resist the temperature increases by inhibiting molecular motion. So the hydrogen bonds, they hold the molecules together, preventing them from evaporating. Now, a solution, we have to look at a solution and a colloid and a suspension. A solution, obviously, all of them, they are solvents, whether a colloid, whether a solution, whether a suspension. So a solution consists of particles called solute. solutes that mix a more abundant substance, usually water, called the solvent. So a solute, it doesn't always have to be a liquid. You could have solid solutes, liquid solutes, and gaseous solutes also. Then if all of, so a colloid is a solution, similar to a solution, but it is more thick. So a solution is excellent in dissolving. It dissolves everything. So that's the solution. But the problem is a colloid did not dissolve everything. So it's a little more thick, little more thick. So a colloid is a mixture of protein and water. So it is not just water, it's a water and protein, like the cytoplasm. It's gel, like gel. So many can change from liquid to gel state within and between the cells. Colloids are defined by the following physical properties. So these are particles that range from 1 to 100 nanometers in size. They scatter light and are usually cloudy. Particles too large to pass through the semi-permeable membrane, and particles remain permanently mixed with the solvent when the mixture stands. Now let's look at a suspension. The suspension has really huge particles, like blood. Now that's the suspension. It is liquid, but it has these big, thick red blood cells in it. So that's not a colloid. That's a suspension or a A suspension is more thick because it has really big. It has really big. It has such a big particles. Now, what's an emulsion? An emulsion is when you have to have liquid in a liquid. You cannot, remember we said a solution can be made up of solutes that are liquid, gas, or solid. But an emulsion, it has to be a liquid in a liquid, like oil vinegar dressing. The oil vinegar dressing, oil is a liquid, vinegar is a liquid, both dissolving in each other. That's an emulsion. That's not a suspension. That's not a colloid. That's not a solution. That's an emulsion. So an emulsion is the suspension of one liquid in another. And examples are oil and vinegar salad dressing and the fat in the breast milk. Fat is liquidy and breast milk, and that's called the colostrum. The colostrum. And that's making the baby drink. If you look in a baby bottle, it's not white milk like the one in the store. It's like a little bit yellowish because of the colostrum fat. There we go. Look at the solution. This is a very interesting model here. Look at a solution. It has really tiny particles. A colloid has what? Proteins. And what's the biggest example of a colloid? The cytoplasm, we said. The cytoplasm, where we said the swimming pool and the rubber duckies. The swimming pool is not made of water, it's a colloid. It is a white jello structure. That's the colloid. A suspension, it has like blood. Blood is an example. So if you're asked on the exam, blood is an example of a colloid, solution, suspension, emulsion. What are you going to say? Suspension. What's an example of an emulsion? Bile? Bile is not an emulsion because in bile you have cholesterol and you have fat. So cholesterol is like a solid. So it's going to be, the bile is going to emulsify the fats. So it's secreted to emulsify the fats. But you said the bile itself. We're looking for an example of a emulsion. So yes, the emulsion can perform emulsification. but the bile itself is made up of stone sometimes. It has the bile substance has cholesterol in it. The best example we just mentioned two: breast milk, fat in breast milk, and also we mentioned what? Oil, vinegar dressing. But the bile is a good answer too. Hmm? Lotion? Lotion. Lotion is, I don't know what lotion is made up of, but I think lotion is not oil in oil. It is oil, is a little thick, right? Lotion is a little thick. It has gas in it also. There's foam in the lotion. Is there foam in the lotion? Depends. There are foam.
So emulsion is just mostly, breast milk.
So any two liquids that are dissolved in each other, that's an emulsion.
That doesn't work.
Hmm? That does dissolve. They have to be dissolving in each other for emulsion to take place. Now, for acids and bases are substances can be acids or bases depending on their tendency to release or bind hydrogen proton. So an acid is a proton donor. So the lower the pH, the more acid you give. The higher the pH, the more acid you bind and the more hydroxyl ions you give. Okay, so if the pH drops, the stronger the acid. And the stronger the acid means the more hydrogen proton it's going to give. It's going to donate a lot.
Nitrogen.
But for basic, the higher the pH. The higher the pH means you're not going to donate hydrogen proton because that makes you an acid. For the base, you're going to donate hydroxyl, OH. That's one definition of a base. The second definition is the more you can bind OH, bind hydrogen. I'm sorry. You donate OH or bind H plus. The acid, fight the acid, bind it, not donate it, bind it, grab it, take it away from the blood. That's an example of a base.
Professor, are you gonna give us a break?
I'm going to give you a break in about 15 minutes. Yeah, I know. It's been 10 hours for me. Okay, so maintain the normal, slightly basic pH of the blood that is crucial for physiological functions, and on the buffers are chemical solutions that resist changes in pH. So pH is the negative algorithm of the hydrogen ion in molarity. And a change of one number on the pH scale represents a 10-fold change in the hydrogen proton concentration. So pH 4 is 10 times as acidic as pH 5. So let's look at the pH scale here. So hydrochloric acid going from 1 to 2, that is a 10-fold increase in acidity. Lemon is really acidic. Wine is more acidic than lemon. Bananas. Water is on the neutral. Milk is a little bit less because milk is the best. You can never eat or drink anything better than milk. No, you get acidic as you go down. So compared to water, I meant. Compared to water, milk is more acidic than water, but it is more basic than bread and less acidic than bread. Yeah, we're trying with hydrochloride. So if you go up, you become less acidic. Yeah. Milk is not acidic. Milk is close to neutral. It is tiny. The acidity of is the pH is 6.3. You're almost neutral. So yes.
If we say
saying that lemon is acidic, and why is it that it's supposed to put lemon in water? Because when you ingest it, it's
When you ingest it, what?
when you mix lemon in water, now it's turned from acidic to alkaline.
No, that was wrong. Lemon is acidic. When you add it to water, water is gonna bring up the pH. So you're not gonna feel that the lemon juice is not gonna make your body more acidic because the water is gonna neutralize the lemon, but it's not gonna make you more alkaline. The alkalinity is here. Is when you eat the egg white. Egg white that is acidic. Yeah, water balances.
Not alkaline, but it's
Yeah.
in the balance.
Yeah, the water is gonna raise the pH.
Yeah.
It's gonna raise the pH, but it's not gonna make it like alkaline. It's gonna raise the pH of the lemon. The water is already neutral. And the lemon is pH 2, so it's gonna bring it up, or pH 3. So we measure concentration by weight per volume, and by percentage, and by molarity, by moles per liter. And our concept of energy. Energy is the capacity to do work. So to do work means to move something, such as a muscle or a molecule. So potential energy is the energy stored in an object. So the food has a lot, the nutrition has potential energy that after you digest it and you absorb it, your body is going to exploit and utilize it. So it has potential energy. But eating ice, pica, that's called pica, crashing ice and eating that. There is no potential energy in the ice for nutritional supply. Chemical energy is the potential energy in molecular bonds, and free energy is the potential energy available in a system to do work. So potential energy is energy stored, but kinetic energy is the energy of motion, so energy of doing work. So examples would be muscle movements, the flow of the ions, the vibration of the eardrum. Heat is an example of kinetic energy. Electromagnetic energy, that's an example of kinetic energy of the photons. And electric energy is both forms of potential and kinetic. So now a chemical reaction that is going to give us, now we're going to learn how we're going to break down these nutritional supplies into a form of energy. So we're going to have to go from reactants to products. So we have different types of reactions. We have decomposition, like catabolism. You eat something big, then you break it down into small parts. You had A, B, C stuck together, then you decompose them into A, separate from B, separate from C. That's the decomposition. Then you have synthesis. When you have A separate, B separate, C separate, then you put them together into ABC, into one big molecule combined. And for that, we use water, we said. If you want to break things down, it's called hydrolysis. You use water to separate A from B from C. And if you want to combine A, B, and C, you remove water, and that will cause them to stick together. And the last type of reaction is exchange. You had A plus B reacting with C. Then you end up with A plus C, and B has been displaced. That's an example of a exchange reaction. That shows you decomposition. AB was 1, it got separated into A plus B. That's a synthesis reaction. There are 2 or more small molecules combined to form a larger one. Exchange reactions is when you have AB plus CD is going to give you, you're going to switch around. You're going to have AC with BD. Even though you started with AB plus CD, you're going to end up with AC plus BD. An example would be stomach acid and sodium bicarbonate from the pancreas, combining to give you sodium chloride and bicarbonate. So now when you look at this starch molecule, that's a polysaccharide. Breaking down starch molecule into glucose molecules, that's an, I'm sorry?
Also,
Okay, all right.
okay.
Okay. Starch molecule is a polysaccharide that's going to be broken down, into smaller parts. So you have a starch molecule. You see here it was big. Now it's chopped up into smaller parts. You see where my mouse is? Your starch molecule got chopped up into smaller parts. What kind of reaction is that? You decompose. That's an example of decomposition. Then you have amino acids. These are little pieces that you bring them together into a bead. You see, now you did not decompose them. What did you do? What kind of reaction is that? Synthesis. You put them together. That's synthesis. But if you look at here, A plus AB and CD reacting, then you end up with AC instead of AB, and you end up with BD instead of CD. So that's a reversible reaction. It can proceed in either direction under different circumstances. It is symbolized with double-headed arrows. So you see carbon dioxide and water are going to give you this carbonic acid, and carbonic acid is going to dissociate into bicarbonate. So reactions can be reversible. So the direction of the reaction is determined by relative abundance of the substance on either side of the equation. So equilibrium is reached when the ratio of the products to reactants is stable.
Yes.
Reactions occur when molecules collide with enough force and correct orientation. In order for the reactions to go to completion, there are factors that affect these reactions, and that is the concentration and the temperature. If you have a lot of concentration of reactants, you will have reaction going into completion. Also the temperature. The more hot the reaction is, the faster and the more you're going to get products. Also the presence of a catalyst. A catalyst is going to speed up the reaction. It's going to make the reaction go faster. So the enzyme catalyst is going to bind the reactant and change their chemical structure to give us a faster product. So I'm going to go, if I have this reaction as a function of time. So here I'm going in unit time. So this is my reactant side, and I go from reactants, obviously, to products. So in order to go from reactants into products, I have to go up this very important EA. EA represents activation energy. EA represents activation energy. So this activation energy is the energy that you gotta pay, is a price you have to pay to go from reactant to product. So now the enzyme, what is the enzyme gonna do? The enzyme is gonna lower the activation energy and help us get to the product side with a lower alternative route. So this is route A. We need route A here in black. Normally, naturally, we take route A. We go all the way up. This is called the transition state complex. Transition state complex up here. Then we go downhill. We go uphill. So what the enzymes do is they reduce the activation energy into this alternative. Now this is called enzyme Enzyme EA, activation energy in the presence of the enzyme. That's the alternative route B. So now you're going to get to product with route B. Who's going to get faster to product? Going up route A or up route B? B. So the enzymes bring down the activation energy and speed up the reactions. That's all that they do. Enzymes only speed up the reaction. Enzymes only speed up, known as catalysis, catalyze the reaction. They only speed up and they only catalyze the reaction. They do not change if you're supposed to get product B from A, they're never going to give you C. So enzymes never change the product. So you're always going to get the same product. Enzymes will repeat the reaction as long as you give them the energy. Enzymes need energy in the form of ATP. It's like a taxi driver. If the taxi gonna drive you from Harlem to Staten Island, when they drop you there, they're not gonna retire. They're gonna make another trip. So the enzymes, they are ready to repeat the react as long as you pay them. Like the taxi driver, you pay him money, you pay the enzyme ATP, will do the job. The second thing is, the enzyme is just like the taxi. You say, drop me in Staten Island, they're not going to say, no, let me take you to Manhattan, it's better. So the same thing with the enzyme. It's supposed to give you B, it's going to give you B. It's not going to give you something else. Okay, so let's take a half-hour break.
Oh, okay, okay. Wow. Oh, no, because I was wondering, I couldn't recognize the face.
Oh, okay.
Yes, yes. How about that? How about that? I need some oxygen.
Go get oxygen.
No, Professor. What's the question I have?
Yeah, I gotta be back.
Which is good for learning, but sometimes it don't take so long for you to touch it. God, I'll get to the side. I'll get to the side. Okay, fine. I might teach a teacher, which is good. So they can be overboard. I don't know.
I'll check it out.
Well, wrap it up on your last long one.
You know, we pass this. Last one. Oh my God. Oh, because I'm at night. All right, social basic. Go back in.
Sometimes stuff depends on what they have done. So how to work I work on you want to work on think it might be sometimes they don't want to work on
Okay.
I know.
Established como posible.
You want to be like me, never have a
Obviously.
Yeah.
All right, one thing.
No, no, mi hermana come back from the You know what I mean? What you make of
Yeah, but we don't have, I don't have any. So right about
Stop them in
I really like how people, she don't like education.
I need to say, yo, you shot.
All the reviews already.
I'll take them to see you like that. What would that She said, she got my short. I said, she said, yeah. One about 50. It is more. No, that'd be funny. I want to get them again. The money actually respond to. No, I really. Yeah, I didn't look at it.
Yeah, I don't know if you don't know. It's not good. No, 6:30 is on time. I'm talking about early, like 6:30 is not. Right on the clock.
Oh, you confident. Anyway, the word. It's still what happened. First, I think we're gonna read them.
Yeah.
I haven't used it in many months.
Like, you know.
Right.
Yo, yeah, what you want? Yeah, they both, yeah, one of them, they were both, one of them, like, it's started. Yeah. Yeah, what about you? Because I didn't idea when I was working in this. I just want to be a shit. I don't know what it was.
First one is just a lot of people.
Somebody. First one.
No, you don't know what the first time was about. Too much. Okay.
No, I don't think
Everybody goes, it's more than just. It's so real. Yes. You know the guy. She doesn't leave me because. I don't know. Yes, there's no, it's like, you know,
like they thought the first week.
Excuse me.
Yeah, I don't know what we're doing.
Everything. Everything you do, they can for you. Anything you do, you know, sir, but what you do. That's why they make it for you to school. For you. And then, yeah, so that's what I was people from. Yeah.
And last time, I'm gonna take what I'm doing. Like a chocolate looking like. No, it's okay. Everything. Thank you very much. Just want to just withdraw.
Lì dove no, no, no,
Figure out. Figure it out. That's when you get a roll.
Any vehicle, any vehicle, we over those. No,
Always have to register it. Yeah.
sure.
Always take it. Yeah. Yeah, I mean, yeah, I'll call you when I. Right. Yeah. On the wall. This one.
I know, right?
Okay. Hello guys, welcome back. Um, so we stopped at the factors that affect the rate. So what do I mean by rate? What is rate? Excellent. So the rate of accumulating. Are you guys following? Okay. So the rate of the reaction is how much product I'm getting. So we said this is really important. What are the factors that determine the speed at which I'm getting my presence, the speed at which I'm getting my products? So we said the presence of an enzyme. The more enzymes I have, the more products obviously I'm going to have, because enzymes speed up the reactions by doing what? Lowering the activation energy barrier. Also the temperature. The hotter the things are, the more things rapidly you're gonna get. And the more concentration of product, the more the rate. But it's gonna reach a ceiling effect. Imagine, these shuttle buses, the shuttle bus when a train is not working. So there's like 5 shuttle buses waiting for people to come out the subway. The more people coming out, the more shuttle buses are gonna be full. It's gonna start the trip. So if you have 100 people coming out the subway, you're gonna get a reaction. A lot of shuttle buses are gonna get filled with people, and people are gonna start. The trip is gonna happen. But if you have 1 million people coming out now, that's too much now. So now it doesn't matter if you add the concentration. You have reached a limit. So you can increase the concentration, which will initially speed up the reaction. But if you add too much, then the reaction rate is not going to be affected. So the concentration increases to a limit. So with the temperature, you heat things up, the reaction is going to go. But if you heat it too much, then that's going to destroy the enzymes. So metabolism is the sum of all the reactions. Catabolism is breaking down macromolecules into micromolecules, and that is going to get energy out. That's known as exergonic. That is exergonic, breaking the covalent bonds to get energy. While anabolism is storing energy within the bonds. And you have oxidative and reductive reactions. So oxidation is losing, Leo says GER. Leo says GER. Leo says GER, G-E-R. Leo is lose electron oxidation. GER is gain electrons reduction. So you oxidize if you lose electrons. So what happens in sodium chloride? Which one is oxidized? Which one is reduced? Because we use deductive reasoning. We know that Leo says GER, lose electron oxidation, gain electron reduction. In sodium chloride, who loses the electrons? Sodium. So who's oxidized? What does the law say? Leo says GER. So Leo is LEO. LEO is if you lose electrons, you're oxidized. If you gain electrons, you are reduction. So sodium lost electrons. Is it reduced or oxidized?
Oxidized.
And chloride gained electrons. Is it reduced or oxidized? It is reduced. There's another law now. If you are oxidized, you become the reducing agent. If you are reduced, you become the oxidizing agent. You cannot be 2 in 1. You cannot be oxidized and the oxidizing agent. Reduced and the reducing agent is the opposite. So if you want to tell which one is the oxidizing agent, you got to do your Leo says GER. If it's oxidized, that means it's the if it's oxidized, that means it is what kind of agent? Oxidizing agent or reducing agent? If you are oxidized, that makes you reducing agent. If you are reduced, that makes you oxidizing agent. Excuse me? Okay. The law says Leo says GER. Lose electron oxidation. Lose electrons oxidation. So if you lose electrons, you're oxidized. Gain electrons reduction. Gain electrons reduction. So in sodium chloride, sodium lost an electron, chloride gained an electron. So chloride is reduced while sodium is oxidized. That's the first law. The second law is if you are reduced, you become the oxidizing agent. And if you're oxidized, you become the reducing agent. So you cannot be two in one. You cannot be oxidized and the oxidizing agent. You cannot be reduced and reducing agent. They are opposite. If you're reduced, you're the oxidizing agent. If you're oxidized, you're the reducing agent. So in sodium chloride, sodium lost an electron. So Leo, it lost an electron, it's oxidized, and then it becomes the reducing agent. Now we have four classes of compounds. We have carbohydrates, we have lipids, we have proteins, and nucleic acids. These are the four families you need to know. Carbohydrates, lipids, proteins, and nucleic acids. So carbon is uniquely suited to form a variety of structures. So carbon is the backbone of these structures. It has 4 valence electrons, and because it has 4 valence electrons, north, south, east, and west, it can form 4 covalent bonds in these 4 directions. It can bind readily with other carbon atoms to form carbon backbones, which are long chains of branched molecules and rings. Readily, this carbon binds readily with hydrogen, oxygen, nitrogen, sulfur, and other elements. Carbon backbones carry a variety of functional groups. These are small clusters of atoms attached to carbon backbone. So they determine many of the properties of the organic molecules, like hydroxyl, methyl. These are the functional groups: hydroxyl, methyl, carboxyl, amino, and the phosphates. So that's the hydroxyl, OH. That's the methyl, CH3. And that's the carboxyl with an OH. Amino is NH2, and phosphate is phosphate. This is phosphate. You got to know these groups. OH is hydroxyl. This is on the exam. This figure is on the lab exam. The OH is the hydroxyl, and these are found in the sugars and the alcohols. Methyl is C with 3 H's, fast oil steroids, and carboxyl is the carbonyl with an OH, found in the amino acids, sugars, and the proteins. Amino has nitrogen with 2 H's. Phosphate, it has the P, this phosphate. So you know that this is the phosphate group. Where we find phosphate? In nucleic acids. That's very important to know, nucleic acids. Macromolecules are large organic molecules with high molecular weights. These are macro. These are big molecules, macromolecules. These are polymers. So molecules made of repetitive series of identical or similar subunits. These are known as monomers. Monomers may be identical or different. So there are polymers made by the joining of the monomers. These are known as the process of dehydration. We remove water, so we join together these macromolecules. So polymerization, as we mentioned here, is done through dehydration, removing of the water, dehydration synthesis. So a hydroxyl group OH is removed from one monomer, and hydrogen H is removed from another. So water is produced as a byproduct, where hydrolysis is the opposite of dehydration. Hydrolysis is the opposite of dehydration, and you have the splitting of the polymer into two different monomers by the addition of water. So an enzyme helps break the covalent bond that links the two monomers together. So a water molecule ionizes into OH minus and H plus. And OH minus is added to one monomer, and H plus is added to another, and that leads to the breakdown of the cleavage. This is a perfect illustration here. Look at dehydration. From dehydration. So we lose water. How do we lose water? We have two monomers. One in blue. You see the blue monomer, number one, and orange monomer of number two. Is that orange or brown? This orange molecule here. So if I want to join them together to make a dimer, from a monomer into dimer, I remove one hydrogen and I remove OH. So I remove H and OH. So they bind together to give me this dimer. To give me this dimer. What if I want to do the opposite now? I want to go from dimer into monomer. I do hydrolysis. So I add water. So on one direction an H comes, on the other direction OH comes. So now they are separated. They are separated. Do you see there? The illustration is very obvious. You had dehydration, you remove H2O. So one is gonna, are you looking at my mouse? Are you looking at the mouse there? Are you looking at where my mouse is? No, you have to look at my mouse because I'm not pointing inside your laptop. I'm pointing there. So if you look here, one is gonna give an OH and the other is gonna give an H. Together, I'm gonna get water to come out, H2O. Then they're gonna be linked. And if I want to split it, I do the opposite. One is going to get an H and the other is going to get an OH, and now they have been split. If you're looking in your computer, I'm not pointing there. It's not going to make sense. You have to look there in that screen. So you see where my mouse is pointing so you can see the dehydration. Again, yeah, so you need to know which process. So if I want to split a polymer, I use hydrolysis. I add water. So I add an OH here. So OH is going to be added here, and H is going to be added here. Then they are separated. And if I want to join them, I remove that water. So by taking OH from one and taking the H from the other, and now I have a dimer. That's the dimer. That's very important. Now let's begin with the first family, that is the carbohydrates. These are hydrophilic organic molecules. They have the general formula of this, CH2O. And this N that's outside is the number of carbon atoms. So for example, glucose is an N, so it's going to be N times carbon, that's N number of carbons. So 6 times carbon, 6 carbons, 6 times hydrogen, there's already 2. So that's got to be 6 times 2, that's 12. And 6 times 1, that's the 6. So we get C6H12O6. That is glucose. But the basic formula is CH2O. There's always a 2-to-1 ratio of hydrogen to oxygen. So always they have O's in the end. Fructose, sucrose, lactose. These are the carbohydrates. So they end up with O's and they have the CH2ON. So they are made up of monosaccharides. These monosaccharides are the simplest carbohydrates, and they are monomers of larger carbohydrates. There are 3 important monomers. These are glucose, galactose, and fructose. These are glucose, galactose, and fructose. They are produced by the digestion of more complex carbohydrates. So glucose is the blood sugar, and we see that these sugars, now we're going to learn why are they important. They are important as a source of energy. Functionally, they store energy. You break down sugars to get ATP, but also we use sugars in the backbone of our DNA. So our DNA has nitrogenous base, it has a phosphate group, and it also has sugar. So sugar is not just for eating, it's also important for the structure of the DNA. Sugar is also important for the structure of the cell membrane. On the surface of the cell membrane, you have sugars that are mixed with proteins known as glycoproteins, a hybrid. They're mixed together, glycoprotein, together, glycoproteins. So this is the structure of the sugars. When you look at something like that, if you see that picture on the exam, I'm not gonna show you like the green one or the yellow or that and ask you, is this glucose or galactose or fructose? I'm never gonna do something like that. But in nature, if you see an orangutan, if you see a chimpanzee, you know that's a monkey. You don't know if it's a orangutan, you don't know if it's a chimpanzee, but you know it's a monkey. So same thing. Looking at something like that, maybe you don't know if it's a fructose or galactose or glucose, but you gotta know that's a sugar. That look like a sugar. The same way when you see a chimpanzee, you see that's a monkey. That's not an elephant. That is not a duck. That is a monkey, generally. So you see something ring like that, you know that's a sugar. That is not a nucleic acid. That is not a lipid. That is not a protein. That is a sugar. You gotta know that. It looks like that. Just from the outside, not in detail. So disaccharides is when I join 2 monosaccharides. So who are my basic monosaccharides? These 3 guys. The glucose, the fructose, and the galactose. I'm not going to show you one and tell you which one is it, but you got to know that they are glucose, fructose, and galactose. They are one ring. But we can join them together. So we can pair, hook up, couple up. We can couple glucose with glucose, and we'll get sucrose. So sucrose is glucose and fructose, while lactose is glucose and galactose. That's the sugar of milk. And maltose is glucose and glucose again. So you see in the 3 different disaccharides, you have glucose in every one of them. But one of them has double glucose. Glucose doubled up, duplicated. Who's that? That's maltose. And that's the sugar of what? The grain, the oatmeal, the barley, the wheat sugar. That is the maltose. Sucrose is the white death, the white sugar, the dangerous sugar, the cancer sugar. That is sucrose, table sugar. It is glucose and fructose together. But lactose is the easiest to know because it has galactose in it. So it's glucose and galactose. Students think because galactose is a longer name, that means it's the bigger one. No. It is the lactose that's bigger. Same way with when we look at the DNA, there is the purine and the pyrimidine. Students think pyrimidine has a longer name, is the bigger. No, it's the purine who's bigger. It has 2 rings, while the pyrimidine has only 1 ring. You see, we joined them. That's sucrose. Sucrose is double ring, so it's a disaccharide. So that's glucose. And who's the second one? Fructose. Glucose and fructose. Lactose, again, glucose and galactose. Maltose is again glucose and glucose. So we pair them up. This bond in the middle that links to us together, the glucose with the that links to us the glucose with the that links for us the glucose with the fructose is called the glycosidic bond. It's very important to know what kind of bond is that called. Glycosidic bond. Yeah, the sugars that are joined together, they couple together. The bond between the husband and the wife is called marriage. Between the sugar is not called marriage, it's called glycosidic bond. That's a marital bond, but this one is not called marital bond, it's called glycosidic bond. When you hear glycosidic bond, you know two sugars are paired together. In the protein, we don't call it glycosidic, we call it peptide bond. When you hear peptide bond, you know two amino acids are coupled together. In the DNA, in the nucleic acids, when two nucleotides are linked together, we don't call them glycosidic bond, we don't call them peptide bond, we call them phosphodiester bond. Phosphodiester bond. Phosphodiester bond. So the biggest example of the sugars that are added up and bundled up in biggest macromolecule is your starch. Starch is made up of huge amounts of glycoside that are linked together, glucose with fructose with in bigger bundles and bundles in your liver stored in your muscle. That is known as glycogen. Then you have starch. Starch is the energy storage in plants that is digestible by humans, and you have cellulose. That is the structural molecule in the plants. You see, this starch, it showed you it has this oxygen. Lipids is the second family. You have saturated lipids and unsaturated lipids. Saturated, they are saturated with what? With hydrogen. Unsaturated, they are not saturated with hydrogen. So lipids come in the form of triglycerides. So now this is the breakdown product. Look, we said, remember, one would give a OH. You see where my mouse is? The glycerol would give an OH while the free fatty acid will give an H. You remove those two, then you connect them together like that. You see how now they're connected? Now that's a macromolecule. You see they are connected by removal of 3 water. So that is dehydration. You see the dehydration? This carbon gave an OH, this oxygen gave an H, removed, make a bond, then this second one also. This one gives an OH, this one gives an H, here gives an OH, gives an H, and then they are all hooked together like that. So now that is an example of a triglyceride, because that's the glycerol backbone. Don't forget that. Don't forget your glycerol. You see where my mouse is pointing? That is the glycerol. And these guys are the free fatty acid. So the free fatty acids are going to be hooked into the glycerol to give me 3-triglycerol. So the phospholipids, they are amphipathic. On their head, they have a choline group and a phosphate, and they have the glycerol. So they have a polar head and they have a hydrophobic tail. They have a polar head and a hydrophobic tail. And these lipids are important for the plasma membrane. So the plasma membrane is amphipathic. What does amphipathic mean? Amphipathic means 2 in 1, is a hybrid. The polar head, thanks to the phosphate group and the choline, and it has a non-polar tail, long free fatty acid. So that's the hydrophobic part. It has a hydrophilic head, polar head, and hydrophobic non-polar tail. Lipids are also important in inflammation for prostaglandins. Prostaglandins are important for mediating pain and inflammation. So that's why when you take an NSAID, the NSAID blocks the cyclooxygenase pathway, so you don't feel the pain because they stop the making and the synthesis of prostaglandins. Prostaglandins irritate the nerve endings. That's how you feel the pain and inflammation. So that's cholesterol has 4 rings. The most distinctive structure of cholesterol is that it has 4 rings, 4 closed rings. And cholesterol is found in the plasma membrane. It gives structural integrity for the plasma membrane, making the plasma membrane thicker, making the plasma membrane stronger. There is good and bad cholesterol. There is good and bad cholesterol. So good cholesterol is one that has a little bit of cholesterol and a lot of protein. So you know blood is polar because remember we said blood is a suspension. It has water in it. And you know the cholesterol is nonpolar. So how are we going to transport this nonpolar cholesterol that we eat in the beef burger, in this lipid and cholesterol? How is it going to go in the blood? So it need a carrier. It need a submarine. So the submarine in the core is going to carry the cholesterol, but from outside is going to be polar to deal with the water. But from the core, from inside, is going to be full of cholesterol. So we have different kind of submarines. There's high density lipoprotein. It is high density because it got more protein than cholesterol. We like that. But if there is the submarine is so full of cholesterol, that means it will have low density because it has now more ratio of cholesterol than protein. We need more big submarine, less cholesterol inside. That's high density. But low density means you have more cholesterol in the inside. That's dangerous. So the bad cholesterol is the LDL. That's going to stick into the blood vessels, clog the blood vessels, prevent the passage of blood. Now we move to peptides. These are proteins. Proteins, these are peptides. And when 2 or more amino acids are joined together, what's the name of the bond we said? Peptide bond. You see the peptide bond? It's just like a glycosidic bond. You see where my mouse? The glycosidic bond is formed by removing of water, dehydration. So is the peptide bond. We remove the hydroxyl group and the hydrogen proton to make a peptide bond. So proteins, when there is a high temperature, they fall apart, they collapse. This is known as denaturation. They denature, they fall apart. So proteins when proteins are made in the ribosome, they are known as the nascent transcript, known as a primary structure, like beads on a string, like the train carts, one after the other. So that's a linear chain. That's a primary structure. The secondary structure, when this primary long bead starts to roll upon itself or make a beta-plated sheet known as alpha helix rolling on itself, alpha helix. Now that's no longer linear. That is alpha rolling. That's known as secondary structure. And beta-pleated sheet, that's an example of when it is in the conformation of a pleated sheet. So that is like a ribbon shape, like a ribbon. So some protein exists as an alpha helix and a beta sheet. These are your collagen in your nails, your keratin in your hair. Then the rolling is not enough. They start folding upon themselves even more to get a tertiary structure, like myoglobin, the protein that is responsible for carrying oxygen in the baby, in the muscle. Then you have a quaternary. That is when you fold even more structures and you join them together like hemoglobin. It has 4 subunits, 2 alpha and 2 beta. So this folding upon itself, going from primary to secondary to tertiary to quaternary, is regulated by bond. covalent bonding, ionic bonding, salt bridges, disulfide bonds, hydrophobic effects. These kinds of bonds is what gonna give my protein the ability to roll and fold upon itself. But the most important structure, primary, secondary, tertiary, or quaternary, is primary. Because they did an experiment, they heat up a quaternary protein. When they heat it up, it fell back. It became tertiary. They heat it up even more. It became secondary. They heat it up even more. It became primary. When they leave it alone, it went right back to quaternary. So they concluded that it is the primary sequence that is going to dictate if you're going to become myoglobin, if you're going to become hemoglobin, what are you exactly going to be? It is your primary, that is your prescription. Are you going to become hemoglobin? Are you going to become myoglobin? Are you going to become alpha helix and beta sheet, beta pleated sheet ribbon like are you going to become keratin? Are you going to become collagen? That's all in the primary structure. So that's the primary structure. You see, beads on a string, sequence of the amino acid. Then they're gonna roll on itself to make alpha helix or make a ribbon like beta pleated sheets. Then a tertiary structure, you have fold interactions between the R groups, and then the quaternary structure, you have four subunits, two are beta and two are alpha. There are prosthetic groups that are covalently bounded to them. So keratin is a tough structural protein of the hair, and you know that's secondary. Collagen is in the deeper layer of the skin, the bone, and the cartilage. Proteins are important for communication. We're going to see that the receptors at the surface of the plasma membrane, these are made up of proteins. For membrane transport, you're going to have ion channels that are going to bring in material and send out material that is known as, for membrane transport, ion channels. They are proteins. They're not sugars. They're proteins. Also enzymes for catalysis. These are proteins. That's how important proteins are. And for hooking cells up, these cell adhesion molecules. Cells, they're not sitting like you guys. Each one is on a separate seat. They're like in an auditorium, in the tissue. They are stuck together, stapled together by these proteins. We talked about that the enzymes, you see what the enzymes do? They lower what? They lower the green. What's the green? The activation energy, EA. Did they affect the red, the net energy? No, they did not affect the net energy. They only affect the activation energy, not the free energy. So the enzyme would take the substrate in the active site and convert it into a product. Enzymes need cofactors. Enzymes need cofactors in order to operate. And you see that there are cofactors, coenzymes need accessory. You cannot work on your own. So enzymes need accessory coenzymes and cofactors, which are usually minerals that help us do the job. And the last family is the nucleic acids. These are the nucleotides. They are made up of a nitrogenous base with a sugar or one or more phosphates. There we go. That's a adenosine triphosphate. That's the ATP. It has, remember, we said the nucleotide must have 3 out of 3. Must have phosphate, must have sugar, and must have a nitrogenous group. So the nitrogenous group here is adenine, but we have adenine, thymine, guanine, cytosine. These are called nitrogenous groups. So adenosine triphosphate is the body's most important energy transfer molecule. And with this ATP is important because it provides phosphate group for kinases. So kinases perform the activation of other enzymes by phosphorylating them, adding a phosphate group to them. Where did they get it from? From ATP. So kinases would take a phosphate group from ATP and add it to another enzyme that is inactive, then it's going to become active. So an enzyme is active. It cannot work. If you add phosphate to it, it will start working. So the kinase will do that job. The kinase will come, take a phosphate from ATP and give it to that inactive enzyme to turn it on and make it work, do its job. So this slide shows you the sources of the ATP. We get ATP from sugars. We get ATP from sugar breakdown. We get ATP from protein breakdown. We get ATP from lipid breakdown. So we get sugar from ATP breakdown we get ATP breakdown from sugars through the process known as glycolysis. You see, that's glycolysis. We break down sugar, glucose to get pyruvate. Then from pyruvate, we get lactate. And you see what we get in the end? ATP. And in aerobic respiration, known as oxidative phosphorylation, that's gonna give us the ATP. So the job of the nucleotide is not just to give us energy like ATP. We have ATP, adenine triphosphate, guanine triphosphate, GTP, cytosine triphosphate, CTP. That shows you they are there for energy. But there are other proteins, there are other nucleotides that are not there for energy. They're there for genetics. So these are your DNA and your RNA, your nucleic acids, your DNAs and your RNAs. We're going to talk more about the DNAs and the RNAs. So these are your macromolecules. Okay, we are done. Let's take the attendance. Yeah, let's take the attendance.